Let's start possibly the most important topic in Calculus 1. We're going to define and motivate and maybe even compute the derivative. But we're going to save most computational examples for next time. Remember the problem that I asked at the beginning of the semester. Suppose at time x, which we will say is measured in seconds, cars traveled this many meters forward. What's the instantaneous rate of change of the car at a specific time, at that instance? That's not a problem we've been equipped to solve. What we do know is, if I think back to middle school, I do remember a formula for rate, right? It was called DIRT. It was distance equals rate times time. I guess if you solved it, it would be rate equals distance over time. I don't know if that rings any bells for anyone. This is called the average velocity. Right? Rate, let me just write that a little neater here. Rate equals distance over time. And really what we call it, instead of distance, we're going to use the term displacement. Right? X represents time. F of x represents displacement. Try to make that D a little nicer looking, right? Now, why do we say distance and displacement instead of distance? You can interchange the two if you like, but the book is going to say displacement because displacement can be positive or negative, whereas distance is only ever positive or zero, you know. You can't have negative distance, whereas you can have negative displacement, right? If you go backwards, that's negative, okay? So anyway, what's going on here? Well, if we draw a graph of the situation, let's get some big axes going right here. I'm going to draw a curve. I'm going to draw the curve. It might be somewhat not to scale, but there's our curve. This is our y equals f of x, right? Which in this, it doesn't really matter, right? I want to be general as possible, but in this case, it equals that, right? Okay. Now, again, not completely to scale, but what we're going to do is we're going to consider this formula right here on the small scale, right? So we're interested in the time x equals 3. And then let's consider some time x that's close to 3. Okay? Now, again, I could have drawn it closer to 3, like, right, I could have drawn it like here, but for illustrative purposes, let's space them out, okay? So anyway, if we look at these points on the graph, then we have 3, comma, just by definition, f of 3. And we can actually compute that. It winds up being 35. How did I get that? Well, I just plugged in 3 right here. Okay. So at time 3, we've traveled 35 meters. Okay. And then sometime x, right, that's after 3, well, I guess we've traveled f of x meters. We don't know what it is, right, but f of x, whatever that is, right? That many meters. Okay, now why did we do this? Well, if we follow the rate formula, let me draw it over here, right? Rate equals displacement over time. Okay? Which in this case, just looking, let me highlight some stuff here, right? This is the displacement, right? It's this distance, it's this difference rather, right? And similarly, the difference in time, right, is going to be this difference, right? Because remember, the y-axis is displacement, and the x-axis is time. Okay? So let's see what we get here. Displacement, just by the definition, is f of x minus f of 3. We could write 35, but I'm going to keep it like f of 3. And then time is going to equal x minus 3. Right, see that? This is just time right here. Right? This time right here. And then this is the displacement. It's this distance right there. Right? That difference. Okay? Now, just want to point out that f of x and f of 3 are y values, and x and 3 are x values. So you could think of this in a sense as like, well, a y value minus another y value divided by an x value, like the corresponding x value minus the corresponding x value. Does that look familiar at all? I hope it does. That's the formula for the slope of the line. The slope of a line, right? Between 2 points. Right? So let me just write slope of a line through x1, y1 and x2, y2. Okay? That's a parenthesis. All right. Now, I just want to point out that we don't really care about the points in particular. We just care about the difference between the y's and the x's. So sometimes we abbreviate it like delta y over delta x. Okay? That's just the notation. But anyway, the line between, these points and these points is going to be this. Let me get my straight line out here. Oh, wait, why did it do that? That's weird. That's pretty good. Okay? It's that line right there. Maybe let me see if I can change it ever so slightly. Massage it just to make it just a little more accurate. Yeah, I think that's pretty good. There you go. Okay. There we go. All right, perfect. That is our line, right? Okay. So this right here is what we call a secant. Secant line with slope f of x minus f of 3 all over x minus 3. So the slope of the secant line is the average velocity between x and between 3 and x. Okay? But we don't want the average velocity. We want the instantaneous velocity, right? So what we do is we shrink this gap, right? We make it smaller. Well, if we make it smaller, then just notice that x minus 3 is getting smaller and f of x minus f of 3 is getting smaller. So really what we're doing, x is getting closer and closer to 3. And there's no reason that I needed to choose x above 3, right? I could have chosen x below 3 and gotten closer and closer that way. So really what we're interested in is, we'll say, to find the instantaneous velocity, we want to find the limit as x approaches 3 of f of x minus f of 3 all over x minus 3. Okay? Now the question is, what happens to the line when we do that? Well, what happens is we get, as this point gets closer and closer and closer to this point, our line becomes closer and closer to what's called a tangent line. And eventually we do in fact get what's called a tangent line, which is this line. Let's see. Let's do that. Let's try to shift that a little bit so it's a tangent line. Perfect. Remember the tangent line? It hits the curve at exactly 1 point. This is the tangent line to y equals f of x at 3, comma f of 3. Okay? So this is this limit right here is the slope of the tangent line. Tangent line to y equals f of x. Whoops, f of x at x equals I'll just say I should just say 3, comma f of 3. Okay. And I don't know if that looks familiar or not, this expression right here. But if you recall, if we go way back to the first class, look at that. I told you that that was the answer. Right? I wasn't just making that up. Right? I told you I'd come back to it. So really what we're trying to find is the limit as x approaches 3 of f of x minus f of 3 all over x minus 3. Or equivalently, I'll just write it the other way, which is the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. Don't worry about this. I'll define it a little bit later. Okay. Actually, you know what? I don't want to write it this way. What I really wanted to write equivalently was the limit as delta x approaches 0 of delta y over delta x. Sorry, that's another way that you might see this written, but I prefer this way. Okay. Anyway, given a curve y equals x and a point a f of a, we say the tangent line to y equals f of x at the point a comma f of a, I guess I should say rather, sorry, I guess the standard notation we say at x equals a is the line through the point a comma f of a with slope, well, exactly what we just said, right? Limit as x approaches a of f of x minus f of a all over x minus a. Right, and remember the tangent line touches only one point on the graph, and it doesn't like go through the point, right? It like grazes the graph, right? So really problem 2 is asking us to find the slope of the tangent line at this chosen point. So remember, again, the first day of class I said that finding the instantaneous rate of change was the same as finding the slope of the tangent line. Well, I hope that this visual explains why. Now, another way to look at this, and this is what I was writing earlier, you can let x equal 3 plus h, and then consider small values of h, that is, consider h approaching 0. So we have that the limit as x approaches 3 of, or I should say, limit as x approaches a, let's say it. No, we'll keep 3 of f of x minus f of 3 all over x minus 3. It turns out another way to write this is the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. Okay? And it turns out this is often easier to work with. Not always, but often enough that the book defines the derivative this way, and we're going to define the derivative this way. Okay? So we define the derivative of f at a to be f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. So yes, believe it or not, this is a limit problem. And one that we can solve. We're not going to use any unfamiliar limit techniques, but it does look weird. So I understand if this is a little bit jarring to look at. There we go. So just to review, I'll write this again, right? F prime of a equals the limit as x approaches a of f of x minus f of a all over x minus a, which equals the limit as h approaches 0 of f of a plus h minus f of a all over h, which equals the limit as delta x approaches 0 of delta y over delta x, which is the derivative. Okay? So another way of asking problem 1 is to say, all right, find the derivative of this function at x equals 3. Well, we don't have the answer, but we do have an expression. So let's try to find it, right? Because we are taking a limit, right? So we can say f prime of 3 equals the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. Now, if you wanted to do the x approaches 3 definition, then you totally can. That's totally fine. I'm going to go ahead and use the 3 plus h definition. I think it's just a little bit easier. Okay. So just to be clear, we're going to find that. Okay? So anyway, when we take the limit, well, we know what f of x is, right? Right? Recall that f of x equals that, right? So what we're going to do is we're just going to plug 3 plus h in for x, right? We're just going to do that, right? So we're going to get 3 plus h squared plus 6 times 3 plus h plus 8 minus, and then f of 3. Well, we already know that that's 35, but if you didn't believe me, you could plug it in, right? 3 squared plus 6 times 3 plus 8, it's 35, right? All divided by h. Now, you don't even need to bother plugging in h equals 0, but if you do, then you'll see what happens is you get 0 over 0. All right, now at this point, there's just no way around it. We have to do a little bit of arithmetic. I don't think any of it is too bad, but we do need to FOIL this. And when you FOIL it, right, pause if you want to do it on your own, but you're going to get 9 plus 6 plus h plus 9 plus 6h plus h squared, and then distribute the 6. Right, we simplify. Now, one thing you might want to notice, is there any way we can simplify this further? Pause the video and take a quick look. Notice that 9 plus 18 plus 8, oh, that's 35. That perfectly cancels like that. It turns out we need that to happen because the problem is h is giving us problems, right? Because we're dividing by 0. We need to factor out that h. And now it turns out we can because we got rid of all the constant terms, right? So it turns out, let's just clean this up a little bit. We're going to have h squared plus 6h all over h. Right? Nope, sorry, I lied about that. H squared plus 12h, right? This guy plus this guy, right? And now I hope you see that we can factor it out, factor out that h. It's going to give us h plus 12 over 1. And then I hope you see that we can just answer it with 12. Now remember, time is measured in seconds. Displacement's measured in meters. So really, we should answer this with 12 meters per second. So what's the instantaneous rate of change at time 3? It's 12 meters per second. And if you remember, way back in the first lecture, I told you the answer would be 12. Remember I said it's 12. Remember I said you could eyeball it. Now, are we really to believe that I just eyeballed all of that and could tell that the answer was 12? Maybe. I'm the professor. But maybe there's a shortcut. Maybe we'll learn that a bit later. Anyway, one more example. Consider an object with position this guy. Write the expression for all these things, right? Pause the video and try to do this. For number 1, the average rate of change. Now, the key word there is average. Average. Right? So from time 4 to 7, so the average rate of change equals the average velocity, which we know equals f of 7 minus f of 4 all over 7 minus 4. And if you plug that in, right, you would just get 7 squared plus 3 times 7 minus 4 squared plus 3 times 4 all over 3. And then when you do it out, you get 49 plus 21. That's 70 minus 28, right, over 3. 70 minus 28 is 42 over 3. So I'm getting 14. And I didn't give you any units, but I think it's 14. Okay? Units of distance minus or divided by units per time. Okay? Number 2, instantaneous rate of change. Okay? Well, that's f prime of 4. F prime of 4, right? That's the derivative. And that's going to equal the limit as h approaches 0 of f of 4 plus h minus f of 4 all over h. Okay? Number 3, the derivative. Well, I think that's actually the same thing. Okay. Number 4, well, I think you maybe are noticing a pattern here. And number 5. Well, not sure what to say other than it's the same thing. So why did I bother doing this? A lot of Calculus 1 is going to be different creative ways of asking you to take the derivative of a function. So you may as well get used to all the different terms. Instantaneous rate of change, derivative, f prime, slope of the tangent line. It's all the same thing. Right? Now, if you want, you can go ahead and try to find that derivative. I'll give you a hint. The answer should be 11.